Let's take a look at polynomial equations and the graphs and polynomial functions in general. So a polynomial is said to be an nth degree polynomial if n is the largest exponent on the polynomial. So here's a very abstract way of looking at a polynomial function. It looks a little scary. All these a sub n minus 1 are just the coefficients, so the numbers in front of the x. And then we have exponents on the x's. All the exponents have to be nice positive integers, and the coefficients have to be real numbers. So an example of a polynomial, 2x to the fourth plus 5x cubed subtract 7x squared plus x subtract pi. Every exponent is a positive integer. Every coefficient is a real number. Irrational numbers are okay, like pi and the square root of 2, but they do have to be real values. We don't have any negative exponents. We don't have any fractional exponents. We're not dividing by x, nothing like that. Any quadratic equation is actually a second degree polynomial because it has degree 2. Any linear equation is a first degree polynomial because it has degree 1. And actually any constant, as simple as it is, can actually be considered a polynomial of degree 0. So again, for polynomials, the coefficients are real numbers, but don't have to necessarily be nice ones. They can be fractions, they can be irrational, and the exponents are all the natural numbers, no negative or fractional exponents. So, vocabulary terms we want to be comfortable with. A 0 is a value of the variable x that makes the function equal 0. So k is a 0 of p of x if p of k equals 0. So it's the solution to an equation if the polynomial is set equal to 0. We can also call them roots, the solution of the equation. And yeah, so not a lot of difference there. Technically, as long as a 0 is a real number, it's also an x-intercept. But you can have zeros that are non-real numbers. Those won't be x-intercepts because they're not real numbers. They don't show up on graphs. They don't show up on real number lines. And then the degree of the polynomial is the value of the largest exponent in the polynomial function. And be in the habit of writing polynomials in standard forms with the terms with the largest exponents coming first, working your way down to the constants. It'll just save you some trouble down the road if you always maintain that habit. Okay, graphs of polynomials are nice, smooth, continuous graphs. Depending on the degree of the polynomial, whether the leading coefficient is positive or negative, will tell you what the end behavior of the polynomial will be. And so it's kind of the long-term behavior. So if p of x is an even degree, so the biggest exponent on the polynomial is an even number, like degree 2, degree 4, degree 6, and its leading coefficient is positive, so the number in front of that x that has the largest exponent, then all the graphs of any polynomial with an even degree and a positive leading coefficient is going to be increasing to the right and increasing to the left. It might bounce around a little in between, but like a nice quadratic equation has an even degree, and if its leading coefficient is positive, it'll look like this. But anything with degree 4, degree 6, degree 12 is going to look something like this. But eventually, as we go off to the right and go off to the left, the function will be increasing. So formally, we say as x approaches infinity, so as x goes off to the right, p of x, the values of y, also approach positive infinity. So it goes shooting up here to the right. And then as x approaches negative infinity, so as the values of x go off here to the left, p of x is just a fancy name for y, approaches positive infinity, so the function increases up here to the left. Now, if p of x has an even degree, but its leading coefficient is negative, the graph's going to flip over and will eventually look like this, decreasing to the right and decreasing to the left. And formally, we say as x approaches infinity, so that's x going off here to the right, p of x, the y values go down towards negative infinity. And then as x approaches negative infinity, as x goes off here to the left, p of x also approaches negative infinity, so it's decreasing here to the left. Now, if we have an odd degree, so that means that the largest exponent on x is something like 3 or 5 or 1, and the leading coefficient is positive, the graph is going to look roughly like this, increasing here to the right, decreasing to the left. And again, formally, we say as x approaches infinity, goes off to the right, the y values approach infinity. But as x approaches negative infinity, the y values approach negative infinity. So it's decreasing on the left, increasing on the right, and then might have some wiggles in between. And then if we have an odd degree and the leading coefficient is negative, the graph's going to flip over and look like this. Increasing on the left, decreasing on the right. And again, the formal way of saying that is x approaches infinity, p of x approaches negative infinity, and as x approaches negative infinity, p of x approaches infinity. So even without doing a graph, we've got a good idea of what a polynomial should look like if we know its degree and what its leading coefficient is, which is really helpful if you're trying to graph it on your calculator, so you know if you've got a complete graph or if you need to increase your window to see more of the graph, because you know eventually to the right it's supposed to be increasing. Okay, so this tells us what the ends of the function looks like. So to find out what's happening in the middle of the function, how much it's bouncing around, we can do a couple of things. One easy thing to do is find the y-intercept by letting x equal 0, so it'll just be the constant. And then the x-intercepts we can find. This is where we're going to take some work possibly. Right now we'll look at easy ones. If the polynomial is factorable, or already in factored form, it's easy to find the x-intercepts just using the zero factor property. So if we have a factored polynomial, f of x equals blah, 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 if we were to FOIL this all out, we'd get 3x cubed plus blah, blah, blah. So this is going to have an odd degree, because the exponent is odd, and a positive leading coefficient because the 3 is positive. So we know it's going to be increasing here to the right, decreasing to the left. But we also can take each of these different factors, set each of these factors equal to 0, and solve, and we get x-intercepts. We have an x-intercept at negative 3, an x-intercept at 1, and an x-intercept at 10/3, so 3 1/3. So I know it's going to pass through these values, and I know it's going to go shooting up to the right, shooting up to the left. So if I connect all that with a smooth continuous line, I know what my graph looks like. Here's another one. So this one is an odd degree and a negative leading coefficient. I can factor out the negative 2x, then this factors fairly easily, and I get my zeros. X equals 0, x equals negative 3, and x equals 2. Because it's an odd degree and a negative leading coefficient, I know the end behavior is going to be increasing on the left, decreasing on the right. So locating my x-intercepts, and then knowing it has to decrease here and increase here, I can connect with a smooth continuous line and have the graph. I can double check that with the calculator, of course. Once you understand how the graphs of polynomials look, it's easy to solve the polynomial inequalities because you can graph them and know where the function is greater than 0 or less than 0. So what we're going to do is start off ignoring that greater than 0 part. We'll just take this polynomial, we'll factor it. Because it's an even degree, a positive understood coefficient of 1, we can locate the x-intercepts at 6 and negative 1. We know it's increasing to the right, increasing on the left, again because it's an even degree and a positive coefficient. And connecting it with a smooth continuous line, we've got a classic graph of a quadratic here, parabola. The vertex is somewhere down here, but we're not actually interested in that. What we are interested in is where is the function greater than 0. That's going to be up here and up here. And it's actually the values of x where it's greater than 0. So p of x is greater than 0 from 6 to infinity, and from negative infinity to negative 1 are the values of x where the y values are positive. Here's one more. Get this out of the way. Okay, x to the fourth plus x squared less than or equal to 0 this time. So again, we can factor it. We get two quadratics. This one gives us x equals 0. This one gives us non-real numbers. So we only have one x-intercept at 0. And because we know it's an even degree, degree 4, positive leading coefficient, we know it has to be increasing. So it's going to look something like this. And the only part where this is less than or equal to 0 is where it actually equals 0 exactly at x equals 0. So that's one very short interval. It's exactly 1 point.